Well, thank you very much for the organizers for the opportunity to give a talk. So I'm going to talk about the stochastic Galerkin methods for the Boltzmann-Poisson system. This is work in collaboration with Clemens Heitzinger from TU Wien. And let me start then. So I'm going to start with the physics, as actually I'm partly a math person, partly a physics person, to give some intuition into the topic. So I'm going to talk about semiconductors, and basically the difference between materials such as metals and insulators is basically due to the band gaps in the energy bands. So for metals, they have very nice, good conductivity because there's an overlap between the energy bands. For insulators, the reason they do not conduct electricity is because there is a big band gap between conduction and valence bands, and the semiconductor is sort of a middle case where essentially there is a gap, but it's not as big. And so you have conduction and valence bands, and this explains a little bit of their properties as materials. The particular materials that we're going to focus on are periodic materials, where essentially you assume a periodic structure, mostly. And then you have a crystal, where it is defined via lattice and atomic basis. And the fact that you have a periodicity in the material in the position space translates into a periodicity in the Fourier space. This is crucial for the model that we're going to present in terms of semiconductors in the next slide. I just want to make you aware that this is part of the assumptions. This is basically a figure relating the periodic structure in silicon, which is actually going to be the material in focus. And now this is the part where I get to the meat of the model. So what I'm going to present is the Boltzmann-Poisson system for semiconductors. This is actually a semi-classical model, which is basically saying that, okay, it has some quantum features, but in principle, you're treating electrons as classical particles. And one has to think that essentially you have a large number of carriers. And so this is an important point because, look, if you think of basically classical mechanics models, you have, say, the Newton formulation, the Hamiltonian formulation, and the phase space density formulation. The phase space density formulation could be done even for a single particle. But the reason phase space formulation, such as the Boltzmann non-equilibrium transport equation, is crucial for a problem is because we have a large number of carriers. And that implies that, for example, we cannot know, even in the semi-classical model, the exact initial condition of all the particles because they're of the order of Avogadro's number. This is why you're forced to use a phase density formulation due to the uncertainty in the initial condition, even in the semi-classical approximation, and you're using a probabilistic formulation via the Boltzmann equation. So in the Boltzmann equation for the non-equilibrium collisional transport, basically you have in the left-hand side a Hamiltonian transport along trajectories in the phase space, and on the right-hand side you have collisions in the momentum space. So the Boltzmann problem, as people is familiar in this workshop, is the balance between transport and collisions. Our model looks classical except for two quantum features. The first quantum feature is that the velocity that you're using as a model for the velocity of the electron is basically the wave velocity of its Schrödinger wave function. So that's basically the wave group velocity, which is highlighted in blue. The other quantum feature that you're going to use in this model is basically that you're using analogs of basically scattering matrices. So your collision operator is basically having a structure which is analog to the quantum scattering of wave function. So this is why I point in blue this analogy between basically the scattering transition matrix in quantum mechanics via these operators. And so the scattering depends basically, or is having as arguments the transitions in terms of momentum vectors and also in the energy, because energy conservation laws are going to guide this scattering process in its physics. And in fact, you can look that I'm putting S times F times 1 minus F prime. So this is basically trying to enforce in the kinetic approximation the Pauli exclusion principle, because you have the probability of being in the state K and the probability of not being in the state K prime. So now in the kinetic formulation, where you have this approximate of the scattering quantum term, you have a gain, which is obeying Pauli exclusion principle, where you have your scattering kernel, which is indicating the transition from K prime to K. This is why you gain a particle. And then the loss, which is also having this Pauli structure. Now, the electrons are charged particles, and that means that they generate a self-consistent electric field. And this is why you have to solve the Poisson equation, where you have the electric field as the minus gradient of the potential, where you need also to know the location of the charges via the density. So you have a time-dependent density that also depends on position. And this interrelation between The Boltzmann collisional transport equation and the Poisson equation is what gives rise to this model for describing electrons moving in semiconductors. For low densities, what you can do is an approximation where you relax your enforcement of Pauli principle and you disregard quadratic terms. And so you have this linear collision operator in terms of F. So you have this structure. And now one important feature of basically electron-phonon scattering in silicon, or basically in semiconductors, is that, well, as I told you, the collision operator has quantum features. And the quantum feature is that you have to obey Planck's laws. And so there are basically energy transitions of two different types: acoustic, which can be approximated as basically having a clean jump in energy, and then optical, where you need a jump of energy h bar omega p, where that is the energy of the phonon needed for the transition for optical scattering. But important part is that you have Dirac deltas. So just as you know from quantization and Planck's laws, that energy conservation has to be exact. And most importantly, this is one of the interesting but also difficult parts of the collision operator for semiconductors, because essentially what you have for your scattering kernel is a distribution. It's not a function. So you have basically Dirac deltas, Dirac distributions enforcing these Planck's laws. One thing to comment is what is NQ is basically the phonon energy distribution, which is usually assuming equilibrium in this model. You could make it as complicated as you want and basically have also time-dependent distribution of phonons, but that's not going to be an assumption of the model. And given these explanations of the collision operator, I just want to mention that this has this structure in terms of the weak form. You can prove, well, if you have your collision operator enforcing the Pauli principle, then the equilibrium distribution, or the basically kernel of the collision operator, would be Fermi-Dirac distributions. Once you enforce, or you do not enforce Pauli and you apply the linearity, the solutions to the collision kernel are basically Maxwellians, as you can see. So that's why you have Maxwellian distributions as the ones that nullify the collision operator. And okay, you have basically this detailed balance principle, even with the Dirac deltas in a weak sense or in a distributional sense. And one typically knows for these models that essentially you have some entropy inequalities because you have a linear operator in the collision. And as long as you have a monotone increasing function, you can prove some entropy properties. And you have basically an L2 type of entropy with the function G equal F divided by the Maxwellian, or the typical Shannon entropy with G proportional to the log. Okay, so let's get to the point of the stochastic formulations. So I was trying, and I will continue making the case that uncertainty is a very important part of this problem. And this is why uncertainty quantification techniques for the Boltzmann-Poisson system is crucial to be studied. The first one, as I mentioned, is basically that you have an initial condition related to a large number of particles. And even in the semi-classical approximation, you cannot know their exact position. And that forces you to basically use statistical formulations such as Boltzmann non-equilibrium distribution. The second one, which I would also like to highlight, is that ultimately, although we're dealing with a semi-classical approximation in the model, this problem is of a quantum nature. And the fact that it is of a quantum nature, as people know from quantum mechanics courses, is that you have uncertainty, and you have uncertainty principle, meaning that you cannot know exactly both the position and momentum. That translates into an uncertainty in the phase space that you would work on. And basically, even if you were to think of a sort of Laplace determinism in the semi-classical approximation, that is not true. So you will never know with complete certainty, the conditions of position space at the position and momentum at the same time. So this is basically telling you that because of the problem is of a quantum nature, uncertainty is inherent to it. You cannot avoid it, even, so basically, okay, I'm making a case here in point 2 that, okay, you have scattering matrices, but I would say that the condition of uncertainty related to the quantum nature is more of a fundamental physics nature. Well, the third one is about uncertainty in the energy band. And the reason I'm highlighting it is because the energy band is crucial in the Boltzmann-Poisson problem, particularly in the Boltzmann equation, because it is guiding both the transport and the collision phenomena. The transport, because, okay, this is giving you by means of the gradient in the momentum, basically the velocity model for the electron. So it has an involvement in the transport part. And then in collision, because it relates to basically the energy conservation via Planck's laws for energy transitions with the Dirac delta. So it appears in the collision term and basically in the argument of the Dirac deltas that are indicating the transition. So if you have a good model for the energy band, okay, you'll probably increase your approximation, but still, first of all, there are analytic models which are approximations. Second of all, you have basically computational models such as empirical pseudo-potential methods, which give you an approximate computational a model of the energy band structure. And so you have to know that this is not exact, and then you might want to study what is the influence of this approximation in the energy band structure that you can know up to a certain point. Okay, phonon energy, you also have some basically deviation between the model and the real world physics, because usually the phonon energy is assumed constant in the model, but actually the experimental evidence in physics tells you that it is not exactly constant. So the fact that it's assumed constant is an approximation that we of course do to basically pick our battles as good mathematicians or physicists, but in principle it is not constant and you're applying some approximation in there. Then, of course, the typical, okay, Poisson parameters, doping permittivity, et cetera, and boundary conditions. So my main selling point in here is that basic uncertainty is very crucial in the Boltzmann-Poisson for main 2 points. Basically, the probabilistic nature due to many particles, and second, the quantum nature fundamentals of the problem. So this basically indicates us the uncertainty study is very important, and we want to manage the stochastic variables, some of the points. So I'm just basically making a case on how, in principle, okay, the stochastic methods, and in particular, the stochastic Galerkin techniques could be useful for this. Well, for the uncertainty in the initial condition, you can introduce a random variable. Basically, okay, for the quantum nature, you can introduce a random variable in the scattering matrix. In principle, if you want to think of this uncertainty principle, you could carry out a random variable for the whole PDF. That's not something I'm commenting here. Then, of course, random variable for the energy band structure, again, because it has influences in the transport part and the collision part. For an energy, it also has some basically randomness due to the constant approximation, which is not completely true. And likewise for the parameters related to the Poisson, such as doping and permittivity, and then the boundary conditions. Okay, so at this point, I'm basically going to comment that, of course, okay, stochastic Galerkin methods have some history going back to Bill and polynomial chaos and the thesis of Gannon and Spanos. But certainly in the last years, stochastic Galerkin and uncertainty quantification has been a very hot topic in kinetic theory. I'm not making an exhaustive list. I'm basically just indicating that this has been a hot topic for the last 6 years or maybe a little bit more. But okay, so we have a review paper by Jingwei Hu and Shi Jin studying UQ for kinetic equations in different applications. One paper that is actually related to this topic of Boltzmann-Poisson by Shi Jin and Liu Liu, basically asymptotically preserving stochastic Galerkin for semiconductor Boltzmann equation. And then one recent paper by Perez Canzanella, where basically they combine Monte Carlo with the stochastic Galerkin techniques, and they study classical gases and in 2 different cases. So, okay, let me give quickly the summary. Probably a good amount of you will be familiar with it, but it doesn't hurt to check it. So I'm going to focus on uncertainty in the collision, basically adding uncertainty in the scattering kernel. And so, okay, we have the general polynomial chaos, where essentially you do an expansion in random variables, and you have the coefficients, which are basically non-random, and then a basis function related to the random variable, and you do an expansion, which is sort of like a Fourier expansion, and then you do a truncation. And so you have the dimensionality, and what you do usually is to choose an orthonormal basis in the random variable, where you have a knowledge of the random distribution, and then basically a family of functions which are orthonormal with respect to the L2 norm induced by that random variable as well. So this is what you have pairings of Hermite and Gaussian, Legendre uniform distribution, Lagrange gamma, et cetera, et cetera. And so the idea of this stochastic Galerkin, as you probably know, is basically that you obtain a system for the expansion of the coefficients. So in principle, you get a deterministic system, which is modeling the coefficients of this expansion in terms of the random variable. But you're going to have a changed collision operator, where you're going to have a scattering kernel, which is obtained via the integration of the randomized scattering kernel with respect to the random variable, and then basically in this norm induced via the random distribution. Okay, so I'm going to present the first application case where what we have is randomness essentially in the phonon energy. So as I told you, and there's a little picture in there illustrating that the phonon energy in principle is known to be not constant experimentally. But okay, as a simple way to basically study this, I'm going to introduce like a little randomness in this assumed constant phonon energy. And that has an impact because essentially that phone energy enters the phone occupation, as you saw in a formula that I presented before, highlighted again. And basically what you're gonna have is randomness appearing in two parts, in the coefficients of the Dirac deltas, but also in the arguments of the Dirac deltas. So this is putting an interesting problem because, well, again, as I highlight, the Dirac deltas are distributions. So this is a little bit of a more complicated problem, or harder to manage in terms of the analysis. But also, well, you know, the random variables appearing on the Dirac distributions. But I think it's a good test case, particularly this one, another for random temperature, because what we ultimately want to study is basically the influence of the uncertainty in the energy band structure both in transport and collisions, although we're focusing here on the collisions only. And this is a good test case by introducing a randomness in an argument that is basically being inside the Dirac delta. So it might not be right now in the energy band structure, it's just in the phone energy, but still operational is having the same effect of randomness and the complexities that arise mathematically. Okay, so this is just a particular application. I'm looking at simple, in fact, the simplest case that you could arise, where basically you're gonna have a system of two coefficients. So basically this is analog of a system of two bands. So you have this expansion where you have basically the mean and a coefficient that is going to give you the variance and the standard deviation. And okay, the system has the structures that I told you. Basically, it's commonalities where you have a new collision operator, where the scattering kernel is obtained by integration in the random variable. And what I'm doing here is basically a little approximation, sort of like a Taylor thing in the random variable, where I have an expansion where I have first sort of a non-random sigma 0 term, and then one which is linear in terms of the random variable. And what effectively the coefficient of the sigma 1 hat is representing is basically like a derivative in terms of the random variable. However, we have Dirac delta, so this is more like a distributional derivative, or ultimately that's what will appear. So, okay, this is my sigma 0. I introduce the randomness. So again, the sigma 1 hat is basically a distributional derivative with respect to z. So what I'm gonna basically use is distributional properties for the derivative of the Dirac delta. And I obtain the sigma 1 coefficient as I'm presenting here. So ultimately, for the implementation, I'm basically gonna have to calculate exactly this. Once I have the knowledge of the distribution, or random distribution, and of course the related basis, which is orthonormal, but this is pretty much the structure that you would get. Okay, so this is one basically particular test case. I mean, you can do this Taylor approximation. You can actually just do the whole thing without the Taylor approximation with the distributional derivatives, but I wanted to present it because I think it's an interesting mathematical problem. Okay, for the lattice temperature, what we're going to do now is assume that uncertainty is actually related to the temperature. And this is a pretty reasonable case if you think about it, because, okay, you have semiconductors, you have transistors and chips, and let's say that you're in a laboratory and you're under experimental conditions and there's a variation in temperature. For example, later on I will present it basically plus minus 10 Celsius degrees. That's quite reasonable. And okay, what we're going to do is focus on basically a parameter called beta, which is the inverse of the normalized temperature. And so we have this random variable introduced in here. So the beta is quite commonly used in statistical mechanics. And basically, again, there's going to be an influence now in the phone occupation. So by having randomness in the temperature, it influences the phone distribution. But this is more manageable operationally because actually here the randomness basically just enters in the coefficients, not in the argument of the Dirac delta. So this is a little change, though we still have Dirac distributions as part of the scattering. And okay, in here, what I'm going to do is basically, again, present a simple test case where you have a system of two bands, which are the coefficients of the stochastic Galerkin expansion. And in this case, what we're going to do is basically present the structure of the collision term that you get for this system. So, okay, this is basically a calculation. You have to integrate your, to obtain this scattering kernel, you have to integrate over the random variable. In here, let me guide you a little bit through the calculations. I'm just going to present basically the results, but I want to give some intuition into what you get. Okay, you perform the integrations basically at the very end. If you see you have a collision matrix structure where, okay, you have your typical basically kinetic collision structure of the operators. Then you have your C plus and C minus, which are basically matrices related to exchange. And in fact, I would like to, I have to present a couple of calculations to give more of the intuition. So for the approximation in here, and to give concrete examples, let's think of the temperature of the environment, which is of the lattice as well, is of 300 kelvins. And I'm going to have a variation of plus minus 10 Celsius degrees. So this is going to be in terms of the parameter beta, basically telling you that the random variable can be in an interval of a fraction of beta, and you want to estimate the n, which is determined in the fraction. What we're going to use is basically a uniform distribution, and then basically use the associated Legendre polynomials. And you have the C matrix that appeared, which is basically going to give you the Q. If you were to solve this, you are going to get polylogarithmic functions. And basically for the calculation of the C matrix, you simply have to use your physical parameters, Planck's constant, etc., estimating the variations of plus minus 10 Celsius degrees. Basically what you estimate is that n has to be of the order of 30. And once you do that, well, you calculate the metrics, which actually, you know, it's of low magnitude in a way. But the structure that I want to present, okay, this is what you would expect typically, right? I mean, you have your new matrix terms and then the exchange, etc. But I like the next explanation of what's happening with the collision matrix, because you can decompose it in two rows. The first row is basically the collision operator as originally written for the deterministic case, but it acts on each separate band. And so basically that first part of the collision matrix is basically not giving recombination across the expansion terms, you know, because you have your mean and you have your coefficient that is representing the variance or the standard deviation. So it is the second term that actually is going to be taking charge of the uncertainty propagation. And what you're going to have is off-diagonal terms which are representing recombination across the two bands of your system. And so this is an estimate. Excuse me. Actually, there is a symmetry between the C plus and C minus because they differ by the identity matrix. So basically, the two terms in here that appear are the same. And okay, so basically the first charge is basically the typical in the deterministic case, no recombination. The second one is having the recombination and is the one taking charge of the propagation of uncertainty. Okay, for this part, what I'm going to present the particular problem of the numerical method that we use, which is basically discontinuous Galerkin. Probably a good amount of you are familiar. I'm simply going to say the intuition and then basically indicate what we're going to use. So this is basically a weak formulation where you want to imitate the hyperbolic nature of transport numerically. And so if you were to think of the simplest example where you have a linear hyperbolic equation with constant coefficients, you know that hyperbolic transport propagates discontinuities. And so if you use discontinuous functions, you can basically model that propagation of discontinuities, but there arises the problem of what is the value of the boundary. And you imitate the physics of transport by basically saying, okay, if I have a discontinuity across a boundary, the information is propagating, for example, in this case, from the left to the right. So the value that I have to choose is basically the value that is being propagated. And so this is how you imitate hyperbolic transport. This is a very simple example. I just want to mention that, of course, there is a long history and work of these methods. The particular method that we're going to use is Runge-Kutta discontinuous Galerkin, which is, as you probably know, basically there's a series of five papers written by Bernardo Cockburn and Shiwan Xu. So those are the type of numerical methods that we're going to use. And well, I mean, my co-authors have worked on this with me and before regarding semiconductor transport, also in plasmas. But this is going to be basically the framework of the numerical method that we're going to use. For semiconductors, in particular for silicon, it's very useful to use a spherical momentum coordinate because you want to center basically along the zero of the conduction band. This is why you use spherical coordinates. And basically you have a transfer Boltzmann equation where you have PDF in the position space, which is Cartesian, and the momentum space, which is spherical. So you have basically a phase space where the momentum has spherical coordinates. So you simply obtain it by multiplying the Boltzmann equation by the Jacobian of the transformation. And this is why you get this new linear collision term. Again, you have your scattering transform and then your Poisson equation in terms of this new density, which is clear that you have this basically probability density function in the new transform space. And to summarize the algorithm, which, well, this is basically a dynamic extension of the commutative map. Again, so basically Irene Gamba, Jose Carrillo, Chi-Wang Xu, Armando Mayorana, and Jingda Shen had worked on this before. So I'm just basically going to use this numerical algorithm. And so the idea of the algorithm is basically that in order to advance to the next time step, you basically first compute the charge density. Then you use it to solve the Poisson equation because, again, you have a self-consistent problem where the electrons, when moving, essentially generate an electric field. And so you want to solve the Poisson equation to basically get the electric field because that's going to give you the transport part of the problem. Once you compute the electric field and therefore the transport, you basically apply the G, and then you obtain a method of lines. And then once you have the G part of the problem, you apply time evolution via Runge-Kutta by an ODE system to propagate to the next time step. So this is why these type of methods are called Runge-Kutta Discontinuous Galerkin. In particular, they have been applied in semiconductors and plasmas, and this is what we're going to use. Okay, to give some quick features, we're going to use a Cartesian grid in this phase space, which is spherical in momentum. We're going to use actually piecewise linear spaces, though here the framework is for general cases. And in here, well, this is indicating you have to calculate the charge density by basically integration over the momentum space, which is reflected by a sum in here numerically. In here, just quickly, the formulation of the discontinuous Galerkin method. Basically, what you do is you apply a weak form, so you multiply by a test function, you integrate by parts, then you have boundary integrals where the same idea of the little example I presented you is being applied in here. So you're going to have these continuous functions, and then there's the question of what is the valid boundaries. And in order to determine the valid boundaries, you basically know what is the direction of propagation of the wave or transport part, and then you evolve the values from the part that is moving to the next cell or neighboring cell. So that's the idea, and the F plus minus are basically the boundary integrals. We're going to use upwind rule, which is basically what I have been indicating by this transport. There are different rules, but this is what we're going to use. We're having linear collision terms, which are pre-computed and stored, and then we're going to apply an RK method, RK2 actually. So this is what we're going to use. For the Poisson problem, for high-dimensional cases, you can use LDG. Actually, we're going to present results for a simple problem, which is 1D in space. So actually here you have an analytic solution. And the only thing that you have to do numerically is basically project that analytic solution, which is an integral solution, in the finite element space of choice. Okay, so some indications of the particular problem that we're going to study is basically a 1D in position and 2D in momentum, because you can use azimuthal symmetry and eliminate one of the variables. So you're going to have an N plus and N plus silicon diode, meaning that basically there is a higher doping in the extremes, and in the middle, which is called the channel, there is a lower doping. So the channel length is 1 micron. The length of the N channel in the middle is 400 nanometers. This is indicating you the difference in the orders of magnitude in the doping in the N plus and the N region. We have azimuthal symmetry, so we eliminate the azimuthal variable, and we have basically as variables the norm of the momentum transformed, and then basically the polar component. So this is our domain, and we are going to have a cut of domain basically for handling the enforcing the zero of the PDF. Okay, the initial condition is going to be basically proportional to a Maxwellian, where we're going to choose a constant so that we have charge neutrality between the density and the doping. Regarding the boundary conditions at the extremes of the 1D device in position, we're going to use something called charge neutrality. And basically, for the Poisson part, what we have is an applied potential bias. So we're having Dirichlet boundary conditions with a difference of potential, so that to make the electrons move. Then we're going to have cutoff boundaries basically at the maximum norm of the momentum. So you make it machine zero. And then, well, it turns out that actually that's the only boundary condition that you need in the momentum space, because what we have done is basically a transformation of momentum from the Cartesian to the spherical coordinate. And because in that transformation, some points have been transformed into boundaries, it turns out that the transport becomes analytically zero there, particularly basically at the poles, for example, or at the origin are equal to zero. So there you do not need to apply boundary conditions. Again, time evolution is RK2. So, okay, let me present the results. And so basically what we have done is combine, we're basically going to solve the system resulting from the stochastic Galerkin formulation via discontinuous Galerkin methods. Okay, so this is basically a figure representing the evolution of the momentum over time over the whole domain, 1D domain for the micron. So you see that there is some stabilization after some basically transient time, so you get a constant current. Then in here, what you have is basically the comparison of the mean moments in the stochastic Galerkin formulation versus the case where you have no uncertainty. So basically, it's a case of the Boltzmann-Poisson system without any random variable. So, okay, you can see that actually in terms of the density and the energy, the difference is negligible or not observable, at least on the plot at the beginning. Likewise for the mean velocity and the electric field. It is actually when you compare the momentum where the difference is very slight, but still there is. So, okay, the electric field is on the left, then basically the momentum, which is proportional to current, is on the right. The difference is basically 2 orders of magnitude below between the mean of the stochastic Galerkin and the case with no randomness. So it is negligible. I mean, then you have to think, well, if you're actually modeling some experimental setting, if your measurement precision is on the order of the difference, right? So that's thinking as physicists, that's something that you would have to consider. Okay, what I have in here is basically a representation of the electron distribution at the final time of the evolution. So things have already stabilized. You have achieved an equilibrium distribution at this point after the non-equilibrium transient. And for visualization purposes, what I'm representing is something akin to a local entropy in here, where you see basically the coefficients of the system. So the F0 or alpha 0 is basically the mean. The F1 is basically representing the variance part. And so, okay, you see basically where the electrons are localized. In this case, the colder colors means more density of electrons, particularly for the F0 case. And in here you see where basically they are more localized close to R equal to 0, particularly highly localized basically in the areas outside the channel. And they diffuse once you basically go outside R and so on. Now, something interesting to mention is that the equilibrium distribution is not Maxwellian, right? I mean, because if it was Maxwellian, it will have a simple relation in terms of the R variable, and it's observable that that is not the case. The right side picture is basically representing the magnitude of the coefficients of the random part, which are the F1 terms. So basically it's indicating you that the magnitude of the random part is basically also in the same regions that I pointed out. Okay, but this is for visualization. If you want to look at the distribution of the particles, meaning the coefficients of the PDF, where the alpha naught is basically giving you the mean, and the F1 again the coefficients of the that give you the variance and so on. You can see. I mean, basically now the warmer regions are representing more density, and of course the regions outside the channel close to R equal to 0 is where you have more particles. As you go far away from R equal to 0, there is an abrupt change, and likewise in terms of the coefficients. So, okay, you can see that the PDF is always non-negative, which is a good thing. And in here, I'm representing basically the mean and the mean I already presented. So here I have the variance and the standard deviation. So it has these patterns. Basically, again, the region of interest is close to R equal to 0. There is a difference in pattern if you look at the warmer colors, because what you're looking is that the junction, which is at 0.3, is actually of interest regarding this variance part. And then once you go past it around 0.7 is basically the polar, well, the pole, which is represented by mu equal to 1, which is of importance. But okay, we're having a quantification of basically the variance and the standard deviation. This is just a comparison of basically the results of our simulation versus a higher order stochastic allocation obtained with 16 sample points. The density pretty much stays constant during the evolution of the problem. But actually there's a good match between basically our stochastic Galerkin and the higher order stochastic allocation. And basically then if you look at the second coefficient of the stochastic Galerkin, which is giving you the standard deviation, and you compare it against the standard deviation obtained by the high order stochastic allocation method, well, here there's a difference. Actually, there's some sort of uncertainty propagation. I mean, they have the same features, but you can see that basically the height and the width of our stochastic Galerkin method increases over time. So here there is a little time evolution. There's also a change in terms of time evolution for the stochastic allocation, but it's less pronounced because they sort of like stay around the same region. But okay, okay, so I'm getting close to the end of the talk. So basically conclusions, what I wanted to highlight is that uncertainty in this problem of Boltzmann-Poisson is crucial by two main reasons. The probabilistic nature of the problem, given that you have many particles, and then the quantum nature of the problem, mainly related to Heisenberg uncertainty principle. You will never know exactly, the initial conditions of the problem or actually the status of the problem. The second thing, okay, we have presented two test cases, which I think are useful from the physics applied mathematics side, because randomness in the phonon energy is a good test case, meaning that, okay, we know that experimentally the phonon energy is not constant and it's basically a scalar problem. So this is a nice test case. And basically for the other part, I think it's also an interesting math problem because randomness in the Fermi golden rule, meaning in these Dirac deltas, basically introduce randomness in the argument of the Dirac distributions. And as far as I know, it is more complicated to basically make the analytic results for stochastic Galerkin techniques in kinetic equations when you have distributions rather than functions which are bounded above and below. And the case with Dirac deltas is pretty much the opposite, right? I mean, if you want to make the approximation via, this physics type of thinking, right? Where you basically have a Gaussian that becomes bigger and bigger. I mean, at some point you cannot bound it. So it's basically the opposite case or the other cases where you have the bounding of the scattering kernel above and below. And well, the other case which we presented, which is randomness in lattice temperature, I also think it's interesting for the physics because look, in the lab, the temperature variations can always happen. And then in applied math, again, you're making the model via scalar random variable and you introduce randomness in operations via the coefficients, not the argument of the deltas. And we are able to basically estimate the variance and the standard deviation for our problem. So this is getting to the end of my talk. So thank you very much to the organizers for the opportunity to talk, Vielen Danke, and hope everybody has a good time in Vienna in the ESI.